is the geodesic width that starts at P and has like the velocity given. And V of P is the subset of all vectors of the tangent space for which C of V is defined at least up to time t equals 1. And this is always an open neighborhood of 0 in the vector space TPS. So the picture is the following. So we have our tangent plane. Let's say that our tangent plane at Tp of S. So somewhere here is our surface of our point P. And then otherwise we have the surface being kind of defined like this. So we have a surface, and at some point of the surface, we choose a point P, and then we take the tangent plane along that point. Then in that plane, we have this subset V of P that gives us vectors. So we have here our, let's say, our V. And then we project it down to the surface. So let's say that we identify this point with this point, and then that C of V. And then at some point, C of V at the endpoint at 1, which is the exponential of P at V. So you essentially you have like the curved object. You can think of that if the picture is not totally clear. So you have like you take the tangent plane to the surface, then you draw a small subset up there, and then you kind of wall it on top. But like the walling will be so that it's given by the geodesics, is that you have to choose like the geodesic that originate in this certain direction, and then you just follow that geodesic, and that might end up like goes around, and then you end up like on the other side of the cylinder maybe. But that's like you go follow the geodesic until the time is equal to 1. And one comment for the name. You may be confused because, like, what is the exponential map there? It's like, it looks very strange. Like, why is that called an exponential map? Is the following. You can think of the real numbers as the tangent map to the circle, or the real numbers we identify with the tangent at this point, P, and then the exponential map in terms of like a certain metric gives you the map that maps T to EET. So that's the complex exponential map, and that one is a geodesic exponential in the sense for one certain way to measure distances on the circle. That comes from this picture. So there's some relationship why that is called exponential map. We need a few more properties of this exponential map. One of them is that we have the following, namely that we can like scale the exponential map of TV is the same thing as CV at the time equals to T for all T that follows essentially since geodesics are unique. So you show that that this one is as well as a geodesic, and then they have to be unique. So you can think of that, morally speaking, as the exponential of P collects all geodesics starting at P. At least locally, it's you always have a geodesic that starts in this in a certain direction, and then you just follow from in this direction using the geodesic. And in fact, there's another observation is that the exponential is actually a diffeomorphism of V of P, the exponential of P defined as a map from V of P is a diffeomorphism of V on P onto a neighborhood of P in S. And that follows essentially by the inverse function theorem. So that says like that a small neighborhood of the tangent space here is identified with a small neighborhood on the surface downstairs. So you have a map that maps from V of P down to the exponential onto this red subset, and like to each point in the red subset, you uniquely get like a V, and to each V you get uniquely a point downstairs. So it's like nice diffeomorphically identified. So in this picture up here means like you have this neighborhood, and then you project it down. Would be like this, something like this part. So V of P, just some part in the tangent space is when one-to-one correspondence to certain points that are close enough to P in the surface. So that's the idea. And using this, we can get polar coordinates as follows. The first step is we choose an orthonormal basis. Orthonormal basis. Let's call it F1 and F2 in the tangent space. That means that we can write every vector in the tangent space canonically as r times cosine phi F1 plus r times sine phi F2 for all non-zero V in the tangent space, and R is bigger than 0, and say phi goes from 0 to 2 pi. With the usual problems that, like, at r equals to 0, that parameterization is not well defined anymore. And then we can transport that to S via the exponential map. And that means that we get phi of at a power point P of r in phi is defined as we take the exponential of P of r cosine phi F1 plus r sine phi F2 which is well defined if r is small enough. So we want r small enough so that this vector up here is an element in V of P. So this one needs to be in V of P, and that we can ensure by having r small enough, and then there's no restrictions on the phi anymore. So it's called the geodesic polar mapping. At P. So the picture here is the following. We choose our point P, and then we have our surface. And what we do is we we take for a given phi, we take a vector that goes in a certain direction that is essentially given by f1 and f2. So the phi gives us the angle with f1. So this direction here would be f1. So the phi gives us the direction, and then we just continue in this direction with it being a geodesic. So that's the geodesic curve, and at a certain radial r, we get a circle, which is r equals to constant. So that would be the polar circle. And these geodesics, these ones are radial geodesics, which would be a phi being constant. So it's really just like the normal ordinary polar coordinates. The difference is that the radial direction is essentially the time that I go in the direction of the geodesic. So it's like how long do I travel along a given direction, and the phi gives essentially which directions do I choose to start with. So that's the picture here. And now we can, some ways, parallelite, like do the same thing as like what we usually do when we have a parametrization of a part of our surface. Is we look at like the frame that is initialized by this these coordinates. So the frame induced by phi is ddr at some point, say q, is given as we take the derivative of our map phi of p in the ddr direction at this time ddr in just like these coordinates r and phi. Then we take the derivative of phi in this direction at the point r and phi, and q has to be connected. R and phi like this. So that's the ddr direction, and ddr phi at q is the same formula, but now we replace the tangent map. So that's just like the same formulas that we had like all over and over. So then it turns out that this frame, dr and d phi, is not like an orthonormal frame, but we have the following, namely that at every point q, if you take ddr, you get 1. So that says that the radial geodesics have unit speed. then we have a second property that says dr and d phi is 0. The geometric interpretation of this is that the radial geodesics are orthogonal to the polar circle. And the next property is that the norm of d phi is strictly positive. Perhaps at q equals p. So where q equals p is anyway like not the best point to look at, because polar coordinates are like very hard to control there. So apart from this point q to p, we have this problem picture is that here we get orthogonality. These geodesic, they hit like the polar circle in a 90-degree angle, and we go up here with like unit speed. So that's the setting. So what we see is this one function, the first fundamental form of which is the norm of the d phi, is the only essentially only interesting function that we have in this case. Phrased differently, the representation of the first fundamental form with respect to the polar coordinates is of the form that we take the pullback, and then we get the matrix, and the matrix is of the form 0, 0, 0, and then we have one function g downstairs for g being a function depending on r and phi, which is so let's have a look at like the geometric meaning of this g, which is the only interesting function that we get in this local representation of the first fundamental form in these very special coordinates. And we have the following. We have P here, and then we look at geodesics. In certain directions. So that all of these are geodesics starting at different points. So let's say here we have phi of P, R of phi. That's one point. Now we change, in order to calculate this, we need to change phi slightly by some epsilon. So here we have, we are sitting on a different geodesic, namely phi plus epsilon, then this vector that like points from here to this point would be epsilon times d phi. So this vector over here is epsilon times d phi. It's like the change of the polar coordinates if I change the point slightly. So that would be about this vector, and g is like the length of this vector appropriately scaled. So that means the distance between phi of p, r of phi, and phi of p, phi of epsilon is approximately the same thing as epsilon times the length of the vector d phi, which we know how to calculate, namely that's the norm with respect to the first fundamental form. d phi. And that one was just by definition a g, so that's epsilon times the square root of g at r of phi. So that means that the square root of g gives you a measure for how far quickly these geodesics spread out. So in particular, if you take the partial derivative of the square root of g with respect to r, and assuming that this one is a positive, so the square root of g is like increasing if I increase r, then the distance between geodesics is increasing. With large R. And thus, the radial geodesics are spreading apart. And that's like actually what you know from the normal polar coordinates. Namely, if you look at the example in the plane, R2 with the standard polar coordinates, if you calculate it, that was one of the homeworks, you actually find that g r phi doesn't depend on phi, but it's just r squared. So that means if you take the square root of that, it scales as r. So that means ddr of the square root of g is 1. So that means they're spreading quite quickly, and that's really like this picture that you know that the geodesics that you go, like if you go out for like large R's, the geodesics are spreading apart from each other. But it might also happen that like for larger R, like they like for some reason converge again, like for like this, because on a different surface. And this behavior is like measured exactly by this square root of g. So this guy here. It's a measure for how they behave like in and there's a bit of a surprising result about this g. Which is given as follows. The theorem is that the square root of g satisfies what is called Jacobi differential equation, which says that if you take 2 times the square root, the derivative of the square root of g in r direction, you get square root of g back scaled with a factor that comes from the Gaussian curvature of the surface. So just like to check that over here, let's say you take the second derivative of the square root of g, we actually get 0. And this is like consistent with this fact. In this case, we get here 0, but also the Gaussian curvature of the plane is 0. So trivially, this equation is satisfied for the plane. So this, and perhaps a bit more geometrically, we also have this Taylor expansion, which is given by the square root of g being r of phi. We can calculate that as, for small r, it's linear in r, then we get a qubit term, which is given by the Gauss curvature at that point. And then the higher terms would be just as r goes to goes like quite large. And p here is phi. Yeah, phi of p, where the radius is going to 0. So that's the expression. So there's this square root of g, which tells you how quickly the geodesic go apart, satisfies like an equation like this, and that says like the rate of spreading of the geodesic of the radial geodesics depends to first order, or depends only on the Gauss curvature. In particular, for if the Gauss curvature is larger than 0, the spreading is slower than on R2. So that gives us a really nice different way of like actually proving the Gauss theorema egregium, that the Gauss curvature is intrinsic, because we can now measure the Gauss curvature in a different way. So you turn around like this proposition or theorem, and actually we can like say, okay, like we can measure the square root of G, and then we can see from that we can calculate the Gaussian curvature. So that's why this is so important. This gives another way to measure K, the Gaussian curvature, intrinsically. Intrinsically, that is, gives another proof that of the Gauss theorem. So the point would be, you start at a point, at some point, and you get some friends over, and then all of you say, like, let's go in different geodesic direction to some fixed radius. So we all go some fixed distance r away from a point P along a geodesic, at least for R like small enough that makes sense. So this gives the polar circle let's call it C of R. So that's the polar circle, and C of R is now just like parameterized by phi, which is a different way of writing the polar coordinates. So that's the circle that goes around like a radius R to something, and then measure the length of that. Of C of R. So let's do that. Then we can go home. So the length of C of R is by definition 0 to 2 pi of the norm of the tangent vector in the phi direction, which is just dd phi. And then we integrate of d phi. So this means it's the same as the square root of g, where we integrate over phi. So now we use, for the square root of g, we use this formula that we had up there. So this is approximately 2 pi of the radius times minus k of the point r to the power of 3 over 6 plus some higher order contributions of the radius, because we get this expansion independent of the phi. So this the expansion over here is like independent of phi. So what you see is that the length of this radius of the circle that we get now, that depends on higher orders in R3, gives us the Gaussian curvature. So we can calculate k of p as the limit as r goes to 0 of this expression where we have 2 pi of r minus the length of the curve. So we subtract this part, then we get after dividing to the power of 3, and then we have to correct like the 2 pi again. So we get this expression. So that means once you know the length of the circle, of this polar circle, then you can calculate the Gaussian curvature again. So that's the connection between these polar coordinates that we get from the geodesics and the Gaussian curvature. And that shows you really like that the geodesics are really sensitive to the Gaussian curvature, and that's also only like the only thing that influences the size of the of these polar circles are completely given in terms of the Gaussian curvature, at least up to the third order. Okay, so thanks a lot. Sorry that it took a little bit longer. So see you next week. Enjoy Christmas if you celebrate Christmas. Otherwise, enjoy doing mathematics homeworks. And then see you next week.
y partial r and partial phi is orthogonal?
It's not like direct. So it's like this. You define. You say like this one is some function.
Yeah.
The norm, or like the scalar product between them.
Yeah.
Then you take the other derivative of that function. You use the formulas that you had that you can put on in a scalar product. Then you use that one of them as a geodesics. For the other one, you turn it around, and then you see that it's 0. So the function is the derivative is 0, and then at r equals to 0, it's essentially just like that. So that gives you then that f has to be 0.
how to prove that there is a unique density along a given dimension?
It's essentially you look at like in polar like in some coordinates. You just take coordinates, and then you write down what it means for a curve to be a geodesic in that coordinates. That's one of your homeworks actually. So that gives you a curve which will then have some x coordinate and some y coordinate. That's the x and y coordinate of the curve. And what you then get is like that this curve is a geodesic. You can only reflect a certain equation here. So what you get is that x and y are like determined, like it's a second order equation. And then you go back to maybe something that you learned in your PE classes. That solution to the equation is very and the initial conditions are of course something like this. So that means like these equations need to that gives